Good morning. I hope the sound's working. Very good. As you noticed, we're running things a little differently today. There is a workshop going on in the other room, and that's why it's a little cozier. We were talking about electricity and light the other day, and very fittingly, the projector broke. So that's why we're going to have to do with the screen today. I'll appreciate that it's a little small, but what I'll try to do is, in strategic locations, zoom like this, and then hopefully that'll work better. The recording's still going to be up, and the recording, of course, will have the screen full screen, and so hopefully if there's something that you didn't catch during the lecture, you'll have a chance to look it up in the recording. Okay. Last time, many things fell into place. We're still talking about electricity, and we saw how the four different kinds of electricity, the one from friction, the one from batteries, the one from animals, and the one from moving magnets, all nicely morphed into just a single form of electricity, as Michael Faraday showed. We also saw that the two big mysterious phenomena, electricity and magnetism, that even the ancient Greeks knew about, and they were puzzled by how similar and yet how dissimilar they were, how they were unified. Because we saw that we can get from electricity to magnetism. If we take a battery and we have an electric current going through a wire, we can make a compass needle turn, compass needle being a magnet. We also saw that we could go in the opposite direction. If we had a magnet that moves, that will in turn generate electricity. So they're really not two different phenomena, they're very, very closely interlinked. These two things taken together, electricity and magnetism, started great developments in telecommunication. Because electricity is something you can run through a wire, and a magnet is something, or a magnetic needle is something you can use to signal. So if you run electricity through a wire and you put a magnetic needle on the other end, you have a needle telegraph, as we saw. Okay, so depending on which of those 5 needles in this case you signal, you can point out a letter to somebody who is hundreds of miles away from you. Then we saw how Sam Morse managed to go a lot further, managed to make it a lot simpler, just needs a single wire, but some set of repeaters to be able to carry the signal over very long distances. And then we saw how people went all the way and they bridged the Atlantic with a single cable, and how they managed to do that in 1858. We also saw how people's notions and understanding of electricity changed. We saw in the early 700s Hawksby's electric spider webs that seemingly are mysterious in space, and you can touch and you can disturb them. We saw how people figured out that there's two kinds of electricities, the positive and the negative, as we call them today. We saw how Ben Franklin's electrical atmospheres entered the scene, and how finally Maxwell's mysterious-seeming vortex model took center stage. That was in the 1860s. Now, Maxwell was a great synthesizer. He took all of the experimental evidence that people had collected at that time, and there was a lot of experimental evidence, and he tried to put it all together. And so, one of the big inputs that he took was from Michael Faraday. Faraday, who paved the way for Maxwell by studying in great detail how magnetic force fields looked like. If you remember his iron filings on a piece of paper with which he made visible these lines of magnetic force that would arise if there is an electric current going through a wire. So that's what Maxwell took. Maxwell also, and he tried to use all of this and make up some model of what must be going on in the empty space inside that wire loop, and that's why he filled that empty space with all of the vortices. Now, likely, Maxwell also tried to see what happens in the empty space between two magnets, where Faraday put his magnetic field lines, Maxwell put his vortices. Why do the magnets repel? Because there are the vortices in the space between the magnets. And of course, electromagnetism. That was, Maxwell's theory was, first and foremost, a theory of electromagnetism, and so it had to also include that translation between the two. Now, Maxwell had a lot more information than this, because by the time Maxwell came around, people had already done extremely precise measurements of both electricity and magnetism. Now, we didn't speak about this last time because we ran out of time at the end, but let me mention it now. There were two people who were fundamental in giving Maxwell that precision data that his theory, his understanding, needed to conform to. One of them was Charles Coulomb in France, and what he did is effectively repeat what Dufay already found, namely that if you have two bodies that both carry the same type of electric charge, positive charge in this case, they would repel. Now, people already understood that if these two bodies are very, very far away, that repelling force would be weaker than if those two bodies were very close together. Now, what Coulomb did is make that precise. He tried to measure how that repelling force changed as a function of the distance between the two bodies. And to do that, he built this wonderful experiment here, which effectively is two metal spheres that are down there, one of which is fixed in place, but it's insulated from the metal of the device. Okay, you can see here, this is like a brass cage, and then you have an insulated rod that carries one of the spheres, the second sphere being suspended from a thin metal thread from all the way up from the apparatus so that the thing could turn. And so if he put electric charge on both of those spheres, they would start repelling, of course, and then he could measure the force, the repulsive force, by the angle by which that torsion balance, as he called it, was turning. Okay, so you can see he put a scale around there where he could simply read off the angle of rotation. And what he found is that as the thing turned, if you make that distance 2 times as large, the force is only a quarter as strong. Okay, this is what's called an inverse square law, and it's very similar to what people had already known from astronomy, because the force that the Earth exerts on the moon and the sun exerts on the Earth follows a very, very similar inverse square law as Isaac Newton found out. Now, another person did the same thing for magnets. And that person, again, was the Frenchman, André-Marie Ampère, who, in a very similar experimental setup, took two coils of wires instead of two spheres, and he would run electric current through both of those coils. And again, there would be some magnetic force that, in this case, would push the two coils together instead of repelling the two spheres. And again, he would try to measure that force as a function of the distance, the initial distance between the two coils. And again, this would be a very, very precise measurement. And so his apparatus was enclosed, if you will, in some cage so that any air currents couldn't influence the measurement. That was the precision to which he was working. And very similar to what we saw in Coulomb's case, one of the coils was fixed to the base of the apparatus, and the other coil was mounted on that big lever arm, and so it could swing back and forth. And so again, as he turned the currents on, that arm would move. Okay, the bottom coil would be attracted to the one that's fixed, and the top of the arm would move the other way. And again, that's what he used to deduce the force. So all of this precision data is what Maxwell had to deal with. And of course, that means he had to take things very carefully and precisely. And his model was not one that he described in words and in vortex, in sort of the sense of vortices, in an oral sense, like I did. But Maxwell was a very careful scientist, and he did all of this in the strict language of mathematics. And that meant that, he had really had to get everything right, because the devil with such precision measurements always sits in the details. You need to get the details correct, otherwise your theory is not useful. And what Maxwell found is that if he took his mathematics seriously, if he really followed through all the consequences that emerged from that vortex idea, then what he had to accept was the irrefutable fact that not only do currents produce magnetic fields, and not only do charges produce electric fields, but it also, in the right circumstances, there can be what he called disturbances in that magnetic medium in which these vortices reside. There could be disturbances that move away from the place where the current sits, something that nobody else had understood before. Now, Maxwell was able to quantitatively, if you will, characterize these disturbances, and he was pointing out that they move at a certain speed that he could calculate. And he said that these disturbances is not something new. This is nothing but light that other people have studied for a very long time, and they just didn't know what they had in front of them. This is what they had in front of them, according to Maxwell. So that means by the time of Maxwell in the 1860s, a lot had happened. Okay, not only did the 4 types of electricity all come together into just one, the electricity, but also magnetism was married together with electricity into what we today call electromagnetism. Okay, you cannot have one without the other, period. And then Maxwell said, okay, electromagnetism in the end is nothing but optics and light. People building telescopes and microscopes and lenses and photographs they knew about light, but Maxwell looked at light from a totally different angle, from the angle of, if you will, an electrical engineer. And so that unification, okay, very disparate phenomena in the end being subsumed in one coherent mental picture, is a huge improvement in how we understand the world. And this is still how, in certain cases, we understand the world today. And of course, such a huge improvement in our understanding is bound to have a lot of consequences. And that's the topic for today. So what are these consequences? The first hero that we need to follow is a German physicist, Heinrich Hertz. Now, he was somebody who was both very good as an experimenter as well as a theorist. He studied in Munich and then in Berlin. He studied mathematics at first and then came into physics, if you will, as an afterthought. And for his doctoral thesis, he tried to apply Maxwell's theory to one specific case. Okay, this was 1880, 20 years after Maxwell came out with his ideas. So there were still many consequences that people didn't understand very well and that had to be figured out. And so this is what Hertz did for his thesis. He calculated what would happen if you took a brass sphere or a metal sphere and you put it in a magnetic field and you turn it very, very rapidly. What would Maxwell's theory predict would happen in that case? Now that was a very elaborate, if you will, technical calculation that allowed him to exert his mathematical muscle, but it wasn't something that he was truly satisfied with. As his doctoral advisor said, Hertz combined theoretical insight with experimental skill. He was really good at both. And so, after his degree, he moved to Kiel, the University of Kiel, where he became a starting faculty in theoretical physics. Now, the university in Kiel didn't really have a lot of experimental facilities in physics, so he was really reduced, if you will, to doing theory, and that made him feel very depressive. He didn't really appreciate the lack of exchange with his experimental colleagues because there was no experimental research going on there. Now, a few years after that, an offer came in from the Karlsruhe Polytechnic University as, they wanted to hire him as a professor in physics. Now, he learned his lesson, and in fact, he had them show them their lab facilities before he accepted the offer. And so they showed him around, and he was satisfied, and so that's how he ended up in Karlsruhe. And so in Karlsruhe, he started going through their storage, where they have all of their lab equipment that they use for lecture demonstrations and so forth. And he found the following object. It's called a Rees induction coil, and it's nothing very complicated. It's just, if you will, 1 Ampere's flat coils of wires, 2 of them, mounted on a common axis so that the distance could be varied. Okay, so you have 1 coil at the bottom, 1 coil at the top, and so they're normally fixed, and you can move them up and down, each coil having its own separate contacts. Now that's something that was widely used in lectures to demonstrate induction. Okay, you can imagine you connect some electricity, a very fast pulse of electricity, to the top coil, and then through Faraday's law of induction, there will be a time-dependent magnetic field, and that will then intersect, as we saw, the magnetic field lines would intersect the coil at the bottom, and according to Faraday's law, if there is a change in the magnetic field lines intersecting the wires of the bottom coil, you would also get electricity induced in the bottom coil. Okay, so far so good. And the nice thing about this as a lecture demonstration was that it was very easily visible. If you applied the electricity at the top coil, you would get a spark in between the contacts, and induction would guarantee that you would also see a spark at the bottom contacts of the coil. And obviously, the students, you in this case, they would find this experiment rather exciting because there's a spark at the top and a spark at the bottom that's seemingly communicated without any connection that's apparent between the 2 coils. And so that's what he did. He played with these induction coils, and to fully understand what he did, we need to talk about how he generated that initial spark that he put up at the top coil. Where does he get, in Hertz's times, where does he get this very fast source of electricity from? Well, he uses another coil. If you think back to what Faraday did, Faraday compiled this big table where he had 1 row for each source of electricity, and then he had 1 column for each, if you will, physical effect of electricity, and he had 1 column that says spark. Whatever electricity is, electricity can produce a spark. And so Maxwell found that, magnetoelectricity is something that's generated through induction, can also produce spark because it is bona fide electricity. And so what Hertz had is what they called an induction coil, very similar to what Faraday started out with. It was simply two separate coils wound around the same base, if you will. It could be a wooden base or a metal base. And you wind two coils, one of which you connect to a battery through a switch, and the other one you leave open. Now what happens, as we know, if you close the switch, some electricity starts to flow through the red coil and would start producing a magnetic field that would go through the second coil and use some electricity in that second coil. Now, the amount of electricity that's induced depends on how quickly that current in the primary coil, the red one, would ramp up, according to Faraday's law. Now, the speed at which the current would ramp up is limited inherently by how the circuit looks like. And so it may not be enough to really cause a sufficiently large pulse of electricity around the secondary coil, but there's, it might not cause a spark, but there will be some electricity. But what you can do, even if you cannot ramp up the electricity fast enough, is you can ram it down almost instantaneously simply by opening the switch. Okay, if you open the switch fast enough, the electricity will drop down to zero almost instantaneously, which will result in a very, very large change, albeit a negative change. And so a very large instantaneous spike of electricity would be induced in the secondary coil. Okay, and then you would get a spark. So that is a way that Hertz and many other people use to generate very, very high voltages in very, very short times, induction coils. And so that's what he used. And he had this rather elaborate apparatus here that I want to show you that he used to drive the two Reese coils. Okay, so he would have his two vertically spaced lecture demonstrating Reese coils, and then he would use his induction coil to drive one of them, the induction coil acting as a source of fast electricity. Okay, and you can see all the elements I just pointed out. There's a battery that provides the source of electricity. It's connected to the primary coil on that induction apparatus through a switch. And on the secondary side, the second coil goes to, in this case, the top of his Reese coils, the lecture demonstrating coils. And in fact, he also inserted a Leyden jar for good measure so that he could store some of that electricity and, in his thinking, make the spark more powerful. And so then what he would do, he'd close the switch, wait until the current would ramp up and stabilize, and then open the switch very, very quickly, and then the spark would appear. And the spark would appear on the primary side, on one of those two coils, and then through induction, the spark would also appear on the secondary side, in the way that we saw, because that's what Faraday's law of induction would guarantee. Okay, there would be magnetic lines of force generated by one coil, and they would intersect the wires in the second coil and produce sparks on both sides. And Hertz got what he wanted, that lecture demonstrating example of sparks being transmitted. Now what he saw in his experiments, and that puzzled him quite a bit, is that the sparking was way stronger than what he imagined or expected. And so that caught his scientific interest, and he tried to see why the sparking was so strong and where that strong sparking was really coming from. And so like any good scientist, he tried to simplify the circuit. Okay? He took his very elaborate setup that he didn't understand why it worked so well, and he tried to remove pieces one by one to see at which point the sparking would stop, or that abnormally large sparking would stop. And so the first thing he did was to remove the Leyden jar. Okay, where previously he had the Leyden jar as an additional, if you will, reservoir of electricity. He removed it, but the sparking stayed very strong. Okay, at this point, he just had the induction coil as the source of his high voltage spikes connected to the Reese coils, that lecture demonstrating coils, but the sparking was as strong as it was before, even without that Leyden jar. The next thing he removed was the coil itself. Okay, so where previously he connected his induction coil, the source of his electricity, to one of those two Reese coils, the top one in this case, which were simply some turns of wires, right, in a flat coil. Now he got rid of that entire coil itself, and he just took the two wires that carried his high voltage, he left them open, and he just, bent the two edges away from each other. Okay, so instead of them going into the coil, he just simply bent them upwards as an open-ended circuit, if you will. And then instead of having that full coil on the other side that would indicate the sparking, he would simply retain a single loop of wire. Okay, a single turn of that coil, if you will, and again, the ends of that coil, the ends of that single turn would be open. And now what it turns out is that there is strong sparking even in that case. And now, he has gotten rid of the coils, and the coils were what, in everybody's mind, was what induction did, or what, allowed induction to happen. And now if the coils are gone, but the sparking continues, Hertz starts asking himself, maybe induction is really not behind this, but something else. Because otherwise, I wouldn't see any sparks anymore. Now here's a picture of what that experimental setup looked like. Okay, what his, if you will, primary coil now looked like. You have the two gaps across which the spark would jump on one of the coils, and it would be here. And then you would have the two wire ends, and he attached two metal spheres on the ends of the wire, okay, sort of to cut them off nicely. And so he was very puzzled, because this was clearly a case that was very abnormal and that nobody had encountered before. Okay, there is something that sparks and abnormally strongly, but there is no coils involved, and so it wasn't clear how induction, if at all, could be behind this. And now he noticed something even stronger, even weirder, because he took his secondary coil, or single loop of wire at this point, and he found that even if he touched it, at the top end, right in between, if you will, the two ends, the spark would still continue to exist. Whereas if he touched it at the end, close to one of the edges, the spark would disappear. Okay, now that's something that confused him even more, because people were thinking of electricity as something that travels through a wire from one end to the other, almost instantaneously. And so it shouldn't matter where I touch the wire, the effect should be exactly the same. Now, Hertz was a very smart gentleman, and he knew that electricity moved along a wire almost instantaneously, but that's one of those cases where the almost is the important part. Because he realized if there was something that oscillated very, very, very rapidly, it could actually make a difference where I touched the wire. Okay, electricity doesn't travel instantaneously, but almost instantaneously so. So if you imagine there being a very fast disturbance on one end, it would take some time, albeit a very, very short time, until that disturbance manifested itself on the other end of the wire. And so in these circumstances, you would actually get a difference in the effect that you would cause by touching the wire in one place or another place. Now, Hertz was the first one to really encounter this phenomenon, and people were not really prepared to think about it in these terms, but Hertz understood what he was having in front of him. And he writes, the middle of the wire here can be touched with the hand without affecting the sparks, but a similar interference at the ends causes the spark to disappear. And here is the explanation that he gave. He says, while the potential, the electrical potential, at the ends oscillates backward and forwards continuously between two limits, it always retains the same mean value in the middle of the circuit. Now what he says is the following. It's a lot easier, he says, if you imagine that closed loop of wire and you unroll it, so you have a straight strip like this with the two ends on the ends, and then the center point is the center point. He says that single coil that I have that gives me the sparks is really like a piece of rope that can oscillate back and forth on the two ends, okay, up and down. But because it oscillates back and forth on the two ends, at the center point it does not oscillate. Okay, this is the point across which the oscillation happens. And so he says, if I touch it here at the center point, I don't affect it at all because there's nothing happening there, right? The ends can keep on oscillating. But if I touch it at the ends, this is when I totally, destroy the oscillation, I dampen out the oscillation, and that's why I don't get a spark if I touch it at the ends, but I continue to get a spark if I touch it in the center. Okay, that explains what he observed, that very strange phenomenon that now suddenly it doesn't make a difference. Now it suddenly does make a difference where you touch the wire, because the oscillation is strongest at the end, and it's zero, it's not existent at all, at the center of the loop. So there was clearly something very different from what anybody else had seen, and so Hertz went on to study it in greater detail. And now by this time he has run out of space in his new lab, so he moved to a lecture hall. Okay, and he says the experiments here were carried out in a large lecture room in which there were no fixtures for a distance of 12 meters. Okay, he has 12 meters of space to work with, and what he does with these 12 meters is he puts the thing that is connected to his induction coil that he calls the primary oscillator. He puts it down, and he takes his single loop of wire in his hands, and he starts moving away from it. And he measures how the sparking changes as a function of where he stands relative to the primary oscillator. And he says, as the distance from the primary oscillator increases, the length of the spark diminishes. Okay, at first rapidly, but afterwards very, very slowly. So what he says is that the further I go away from the source of whatever is causing the sparks, the weaker the sparks become. But they don't get uniformly weaker, but at first they get weaker very, very quickly, and then they sort of, drop off a lot more slowly. And that means, and he recognizes that there must be two different effects in play. Okay, he says it's not true that induction is not at all responsible, but he says that induction is responsible, but it dominates, it's the strongest effect if I'm very, very close to my primary oscillator. But then as I move a step or two away, the effect by induction is almost imperceptible, and there's something else that takes over. And it's that something else that keeps it alive, for several meters. I can move away for several meters. Induction is not important, but something else is there that keeps the spark going. And so by this time, he clearly has in his picture the phenomenon of some sort of wave emanating from his primary oscillator, and he tries now to make the wave visible. Okay? And to his good fortune, that lecture hall had on one side of it, if you will, a series of metal pillars that held up the roof of the lecture hall. Now, metal, as we learned, is a very good electrical conductor. So to the electricity in the waves that he supposes to be there, that series of metal piles acts as a solid wall that would reflect whatever electric waves would hit it. Okay? And then he says you get sort of this coffee cup phenomenon, where if you excite the wave at the center of the coffee cup, it propagates outwards, it will hit the wall, and it will be reflected back. And then what you have is this very nice pattern of standing waves that oscillate up and down that arises through the very complicated interaction of the wave coming out and the wave coming back in that is reflected. And so he says, just like I would expect to see this up and down pattern in a coffee mug, I should also see this up and down pattern in my lecture hall, because there will be a wave emanating from the primary oscillator, hitting the wall and then being reflected. So I have the exact same situation that I have in my coffee mug. And indeed what he observes is he takes his wire, that single loop of coil that he uses to detect the presence of the wave, and he puts himself down and he sees the spark. And then he takes a step and there is no spark. And he takes another step and the spark reappears. So as he walks, if you will, from the center of the coffee mug outwards, he really sees, spark, no spark, spark, no spark. Exactly what he would expect if there was really a wave moving out and then moving back in. And Hertz says, aha, in 1887, he says, this is very nice, but I'm not actually the first one to do this, because the optics people and the acoustics people have done that a long time before me. He says, in optics and acoustics, these experiments, observing these standing waves like in a coffee mug, in those fields, these experiments count as arguments in favor of the wave nature of either light or sound. And so the phenomena that I described may be regarded as arguments in favor of the propagation of an electric oscillation by wave motion. So he says, what I have here is exactly the same thing that other people have seen way before me in water, right, in a coffee mug, or in light, and that those people have used to argue for the existence of light or pressure waves in a liquid or in a solid, for the existence of the wave nature of these things, and so I can do the same here. And in fact, this counts as a demonstration of the existence of electric waves that are emanated from that primary oscillator. And so, electromagnetic waves exist. That's what his conclusion was. Electromagnetic waves exist, and here is a sketch of how he made this discovery. His primary oscillator on the table, hooked up to the induction coil underneath, which in turn is connected to the batteries, and there he is, with a single loop of wire in his hands observing the spark. And there would be a simultaneous spark here at the table and in his hand. And then he made, if you will, the probably biggest understatement of the century, when he said, it is of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see with the naked eye, but they're there. Because Hertz was very much the scientist. He was thrilled by having made this discovery, but he didn't see beyond the discovery. Now, other people did see beyond the discovery, and one of those people was Guglielmo Marconi, an Italian, who was growing up. He was the son of a very rich family, a wealthy landowner close to Bologna in Italy, and he grew up on the large countryside mansion of his family. Now, he was, at the beginning, tutored by sort of private teachers that his parents would hire, but he always wanted to know more than what they were able to teach him. And good fortune would have it that their mansion had a large scientific library. And so he would really immerse himself and read about steam engines and electricity and also history, and so learn and teach himself a lot of what these books had to offer. Now, his father's health wasn't the best, and so his parents, his entire family, in fact, they moved south during the winter months to enjoy sort of the more mild climate of the south of Italy, and they went to two places regularly, to Livorno and back to Bologna. And in both places, he started building relationships with academics. Okay, he met Vincenzo Rosa and Augusto Righi, who were both university professors, and they started mentoring him. And he never was enrolled as a student, but he had close contact with both of them, and they would start teaching him what they know. Later on, he would actually sit into some university lectures, again, without being enrolled as a student. He simply wanted to learn all that the world had to offer him. Now, he was very big in the sciences, and even his middle school teacher recognized that. But they also recognized that, they reprimanded him, in fact, that it's necessary to improve your pronunciation of Italian, my dear boy. Okay, he was very good in science, but not so much in Italian. But he saw the opportunity where others did not see it. And in fact, he started playing with Hertzian waves, as they were called then. Okay, and he started reproducing some of Hertz's experiments, and he started building his own little radio transmitters. Okay, so he says, this was in 1895, a few years after Hertz had made his discovery, 15 years after. At my home near Bologna, in Italy, I commenced early in 1895 to carry out tests and experiments with the object of determining whether it would be possible, by means of Hertzian waves, to transmit to a distance telegraphic signs and symbols without the aid of connecting wires. Okay, so from the very beginning, he has this idea that what Hertz didn't deem possible, namely to use these sparks that would appear on two coils separated by a long distance to transmit information, like a telegraph. And his setup, you can see, very much consisted of the same parts that we saw in Hertz's setup. There would be the battery at the bottom, there would be a big induction coil, there would be the switch that would open and close, and there would be the gap across which the spark would jump, and that would be connected to his antenna. Now, his antenna looked a bit different from what Hertz used. While Hertz simply bent the wire ends outwards and connected them to two metal spheres, he simply took a piece of metal foil and sort of, hung it up there. And he says, with this simple setup, his first test that he used an ordinary Hertz oscillator for, as he called it, with that apparatus, he was already able to telegraph up to a distance of about half a mile. Okay, that's not bad for a first try, but it's obviously nothing that, the establishment of wire telegraph operators would take notice of. Now, you might wonder, we've just seen how he transmitted his signals, but how did he receive it? How could he telegraph over the distance of half a mile if he didn't have a receiver? Now, in fact, he did have a receiver, and it is what we call today a coherer receiver. And in fact, its simplicity itself, if you look at this picture here, it's simply a glass tube with very, very fine metal filings inside, okay, touched by two metal electrodes that are then connected to the ends. Now, if this is, very, very small iron filings, what would happen is that they oxidate, okay, they rust on the surface, and so normally there would not be a conducting path of electricity across the two terminals of the coherer. Okay, that fine metal dust would simply not conduct electricity because the surface of all of the small metal grains would be insulating. Now, it turns out that as soon as a radio wave or a Hertzian wave would sort of reach the apparatus from the outside, that those small metal filings would spontaneously rearrange themselves and would actually allow if you will, a slow or direct current to pass through the coherer. Okay? And after that had happened, you had to tap somehow the glass to, break apart that conducting path again and ready the device to detect the next pulse of electricity. Okay, so the fast, very fast oscillations from the Hertzian waves would come in. They would rearrange the metal filings to make a very slow conducting path of electricity through the device, a direct current path, and that's how it would detect the fast waves. Now, it turns out that coherer wasn't very reliable, and people complained a lot that it was publicized as wonderful, but it was actually wonderfully erratic and bad. It wouldn't work when it should, and it worked overtime when it shouldn't have. Okay, so these first radio transmissions, they were everything but reliable. But in August 1895, he discovered a different arrangement which improved things a lot. Namely, it improved the distance a lot over which he could communicate. And he did that simply by raising his antenna upwards. Okay, he builds a small, if you will, pole here, at the top of which he puts up his antenna. And the second big improvement that he makes is that the second part, the second coil, if you will, the second terminal of his induction coil, one of which would go to the antenna, the other one he would connect to ground. Now, he didn't know why that would make things suddenly work so well, but it did. Okay, today we know why it does work. Marconi didn't know, but it worked nonetheless. And with that setup, he could communicate over a lot greater distances, and in fact, communication was possible even if there are obstacles in between the transmitter and the receiver station. Okay, you did not need a direct line of sight to communicate. And that means now suddenly people started seeing the value of this. In 1897, the distance of communication was extended to 4 miles, and in May of the same year to 9 miles. And now here actually are a few employees of the British Telegraph Company checking out some of Marconi's equipment. And you can see what they have. There is, again, the induction coil, and there is the pole that goes up to the antenna, and then this gentleman operates the switch. So people started taking notice, and soon, in 1899, in fact, they were able to send signals across the English Channel, okay, from Dover down to France. And in 1901, only 43 years after the first transatlantic cable was inaugurated and then broke down 3 weeks after, he managed to send signals across the Atlantic for the first time. And obviously, this required substantially larger equipment, substantially higher antennas, and he built this massive transmitting station in England. And then in Newfoundland and St. John's, actually very close to where that first transatlantic cable hit land, he put up the receiver station. And similarly, he had to have the receiving antenna very, very high up. Now, he couldn't build a massive station like he did in England, so what he had, here is Marconi, he had his associates fly up a kite on which the antenna was mounted. And through that system, they were in fact able to communicate wirelessly across the Atlantic. And the rest, if you will, is history as far as electricity goes. 1880, 1900s, electricity starts to become a commonplace sight. New York City was electrified. In Tennessee, the Centennial Exposition featured a very large light show. People were able to generate and transmit electricity in the very same way through induction, but on much, much larger scales. Also, the state of the art of radio communication was improved a lot. These coherer receivers soon became out of fashion because they continued to be unreliable. People now used small little crystals. The crystal receiver was invented. And in 1954, after the war, the first transistor radio hit the market. And today, electricity is really everywhere. Okay, it comes out of the outlet. It powers my computer. It powers the screen. Today, we know where it comes from. It comes from magnets that spin, as Faraday taught us. And it comes to us through magnetic wires, like Stephen Gray taught us in his first experiments. You might still have sort of a lingering doubt about what the actual nature of electricity is. Now, we saw how Maxwell described all of this, and Maxwell is what we still use today, and in fact, it applies to all of the situations we discussed. But, you might think, are these vortices of Maxwell really all there is to it? Or is there not something else? And in fact, there is something else, and to discover it, we need to jump on a different storyline, and we need to go back to Michael Faraday for a second. Now, if you remember, Michael Faraday did many things. He made visible these magnetic lines of force that set the road for Maxwell. He was able to convert electricity and magnetism back and forth, and he also had his big compiled table about all the effects of electricity. Now, if you will, we already pointed out, one column here was sparks. He wanted to show that whatever the source of electricity, if it was bona fide electricity, it could produce sparks. And so Faraday wouldn't be Faraday if he limited himself to simply ticking a few boxes in a table. In fact, he studied sparks in great detail. He studied how electrical sparks change their appearance depending on the surfaces between which they were energized. Okay, if you take two wires, eventually you will get a spark. If you use two, if you will, brass balls, he calls the phenomena exceedingly interesting. If you have sort of a very fine tip, the spark would branch out like a lightning strike all around the room, all of which are phenomena that Faraday studied. And so, in 1838, that was a few years after he did his induction experiments, he continued looking into discharges, spark discharges and other discharges, and by this time, vacuum pumps were very widespread. So Faraday and many others, in fact, started understanding or studying what happened if you sent electricity not through a spark in the air, but through electrodes in a vessel from which you evacuate the air. Okay, a vessel with which is filled with rarefied gases, as they call it, dilute gases. And they would notice, this wonderfully beautiful phenomena. Okay, a brass ball, he says, being made positively electric in an air pump receiver, if you will, a glass jar from which he pumps out the air, he could cover it all over with this wonderful purple glow if he connected it to a battery. In fact, he continued studying these discharges, and they were very, very puzzling to him because they turned out to be very diverse. Now, one of the things he noticed is that if you take an elongated glass tube like this, with both electrodes on either side, it wouldn't actually be filled with a continuous glow of discharge, but there would be some intricate structure to it. There would be some glow very close to one side, and there would be a dark gap, and then you would have this continuous column of glow. Now, people didn't understand why this dark space appeared, but even today we call it the Faraday dark space, and today we understand where it comes from. Now, other people took over. One of them was Gastiot, who was a wealthy wine merchant by day, and he was an amateur scientist by night, and he also did similar experiments. And you can see his experimental apparatus here is very similar to what Faraday used. Again, he has his glass vessel, which he would connect to an air pump, and he would use an induction coil, much like Hertz used. Close the circuit, open the circuit, you get a quick spark to trigger the discharge in the glass vessel. Now, he discovered even more intricate phenomena. If you look in the discharge, he pointed out that the quality and the structure and the appearance of that discharge depended a lot on what the remaining pressure of the gas was inside. Okay, at relatively high pressures, you would get some continuous glow discharge, like here, but if you reduce the pressure, you would not only see one dark space, but this repeated bright, dark, bright, dark, bright, dark pattern. Now, none of them realized back then, but today we call this field plasma physics. And plasma physics is as diverse today as it was back then, and it spans many different applications and across many orders, if you will, of magnitude. It shows up in satellites where plasma is ejected from a rocket nozzle to generate thrust and provide very, very finely controlled maneuverability to satellites. We use it to treat plastic surfaces today, so we can write on them, and the ink of the pen actually sticks. In a metal workshop, you will see a plasma cutter, if you want to cut thick metal sheets. And in the generation of electricity, fusion, nuclear fusion, also uses plasmas. Now, this is what we can do today with all of our technology that we have that people back then didn't have. Now, it turns out progress in the study of plasmas and in these discharges was strongly linked with progress in the quality of the air pumps that people used. Because all of those phenomena only appeared if you really are able to dilute the gas as much as they were able to. Now, the next gentleman that we should talk about is William Crookes in Britain, who had the advantage that he had access to a much better vacuum pump. It was invented by the German chemist Sprengel, and it worked differently from the mechanical pumps that all of his contemporaries used. Okay, mechanical pumps much like the one that you would use to inflate your bicycle tire, but operated in reverse. Now, Crookes' pump, or Sprengel's pump actually, worked a bit differently. It worked in the following way. You had two reservoirs filled with mercury, one at the top and one at the bottom, and there would be a vertical pipe connecting the two reservoirs, and the vessel from which you wanted to evacuate the air would be branching off, sort of that vertical pipe. And obviously, like in many places, that mercury would sort of start dropping down, and the mercury drops, as they pass this branching point, they would carry some of the air molecules with them and carry them down the pump, in which way you could evacuate that vacuum vessel. In fact, you could achieve much higher exhaustions, as people call them. You were able to remove much more of the air than with that simple mechanical pump. Now, William Crookes noticed a different phenomenon that only appears at extremely low residual pressures. Okay, when the exhaustion approaches 30 millionth of an atmosphere, okay, so only 30 millionth of all of the air molecules inside were remaining, a new phenomenon makes an appearance. Okay, he found that from the negative terminal, from the negative metal surface inside his glass tube, it looked as if there were molecular rays, some new phenomenon that seems to be moving along straight lines and that seems to be coming from that negative terminal. And he called it molecular rays. We'll see in a second why that name is not appropriate, but this is what it looked like. So here's one of Crookes' tubes with the negative side at the back and the positive side down here. This is also where the pump would be connected. Okay, then now you can see this, again, pinkish purple glow, but this is not what Crookes pointed out. That's simply the residual gas discharge that you would always have. But what Crookes was fascinated by is this greenish glow on the far side that seemed to be on the opposite side of that negative terminal, and that seemed to be caused by something moving along straight lines, in fact, because it casts a shadow. If you put some metal object inside, you would see the shadow of that metal object that, the rays would cast. And in fact, he pointed out, these molecular rays, which give rise to that greenish light, they absolutely refuse to take a corner, as he called it, and they really want to move in straight lines so that whatever object you put in, you will get a shadow. Now, he also figured out that you could actually deflect these mysterious rays. They would move straight if you let them, but if you move a magnet close, they would actually start bending. And depending on where you move the magnet, further away or closer towards the tube, that deflection would get stronger or weaker. And in fact, if you put the magnet one way, the rays would sort of start bending upwards, and the shadow would move as the rays moved upwards. And as you put the magnet the other way, the rays would move downwards, and the shadow would move downwards with them. Okay, so whatever was happening was moving along straight lines, but it could be deflected. Now, Crookes called it molecular rays, and he called it molecular rays because these were the times when molecules were very much in fashion. If you think back, the second half of the 1800s was when the kinetic theory of heat became widely adopted, and when people realized that heat is not a substance in itself, it's not caloric as we saw, but heat is simply the agitation and the movement of molecules. And James Joule, in 1850, made that notion precise. Now that means William Crookes, in 1880 or 1878, he would of course knew that. He would of course know about the true nature of gases, and in fact he writes in his report about the modern idea of the gaseous state of matter. It's nothing but the fact that there's millions of gas molecules inside his tube that are in rapid motion in all directions, each of them having millions of encounters in a second. Okay, so you have all of those gas molecules that you couldn't pump out, and they would move around, and they would hit each other, and they would hit the wall of the tube, and so on and so forth. And then he pointed out that as you remove more and more of those air molecules, because you remove the air, these collisions between the molecules would get less and less and less frequent. In fact, by great rarefaction, he said, the hits become negligible in comparison to the misses. If you have fewer molecules, they start missing each other more and more and more, and they start hitting each other less and less and less. And so, the average molecule, he says, is allowed to just move in between collisions along a straight line. And if the time in between collisions got longer and longer and longer because they started missing each other more and more and more and more, you could get, in fact, that phenomenon where things move along straight lines. And that's why he called it, in the beginning, molecular rays. Molecules were very much in fashion, and people were able to explain the notion of heat by invoking the idea of molecules, so it was natural that they also tried to explain everything else with molecules, such as his molecular rays. But in fact, Crookes got it all wrong. And it's sort of already, with the benefit of hindsight, we can see why he got it wrong. What he says is perfectly true. Things move in a straight line in between collisions, but that had nothing to do whatsoever with electricity, right? So what's the connection with electricity? He simply says that if there's a gas molecule, it moves along straight lines, whether there is electricity or there isn't. So there's still a mystery. Now, the next step towards solving that mystery came from another gentleman in Germany, Wilhelm Conrad Röntgen, who was a professor at the University of Würzburg. And now these were the days where everybody was experimenting with these discharge tubes, and they were trying to figure out what the nature of these molecular rays was. Now, in these days, people already called them cathode rays instead of molecular rays because they still emanated from the negative side of the tube, and the negative side of the tube was called the cathode. And so because they still didn't know what the nature was, they simply called them from where they're produced, namely the cathode. Now, there was an idea that people had that maybe it's easier to study the nature of these rays if we were able to get them out of the tube. But the problem was that these rays are only produced if you're able to exhaust much of the atmosphere, and so you couldn't simply drill a hole in the tube, because that would simply make the air rush back into it, and the rays would disappear. So what they did is drill a small hole in the glass, and then seal it again with very, very thin metal foil that would allow the rays to pass, but would prevent the air from rushing back into the tube. And so Röntgen would have one of those tubes in his lab, like many people, and he would experiment with it. And what comes next is, again, one of those ubiquitous serendipitous discoveries, when he looked at the discharge from a large induction coil, like everybody else did, through a well-exhausted Crookes tube. Okay, he repeats something that many people had done before him, and because he wanted to study, if you will, if that greenish glow on the far side of the tube was persistent, he covered the tube with a light-tight box. Okay, he closes it with a close-fitting shield of black paper, as he says. And then on the far side of the lab, he has something that we don't know exactly why he had it, but it might have simply been a leftover from the previous tenant of the lab, and that is a fluorescent screen. A piece of paper covered with barium platinocyanide, okay, which sounds very complicated, but it's in fact something that was very common in those days. Looks like a yellowish powder if you have chemically purified it. And many people used substances like this and many others in lecture demonstrations, because they found that if you put these materials into the tube, you did the opposite. You weren't trying to get the rays out, but you sort of put something into it so it could be hit by the rays, and then these wonderfully beautiful, colorful effects would follow. These fluorescent effects would follow. So now he had the screen covered with this fluorescent material, and he noticed that as soon as he turned the discharge on, that screen on the far side of the lab would start to glow. And the sentence that he writes next, although he puts it in a scientific paper, in my mind could actually come out of a poem. He says, "A yellowish green light spread all over its surface in clouds, waves, and flashes. The luminescence trembled, wavered, and floated over the paper in rhythm with the snapping of the discharge." He was clearly taken aback by the beauty of what he saw. Okay, this like rhythmic fluorescence of the screen was very much in sync with what the discharge inside the tube did, through the paper. And he noticed that whatever comes out, it goes through the paper, and it's clear to him that there is something that is able to penetrate and that he needs to study. And so he studies it by putting obstacles in his place. He puts another sheet of paper, and he finds it's very transparent. To whatever rays come out, nothing changes. He puts pieces of wood, and still nothing changes. The fluorescence continues. He puts aluminum, 15 millimeters thick, and that still allowed the rays to pass, albeit slightly reduced the fluorescence. Now, at this point, he already started calling them X-rays for the sake of brevity, as he points out. He doesn't know what they are, he simply calls them X-rays. And then there is also this sentence in the very same paper that, if you will, is another marvelous sentence in the opposite sense. He writes it in a very monotone way, but it signifies great importance. "If the hand be held before the fluorescent screen, the shadow shows the bones darkly, with only faint outlines of the surrounding tissues. Okay, he did the first X-ray image in history, and it was actually the hand of his wife that he put to take this image, and she was wearing a ring. That's why you see this little shadow of the ring, but you can clearly see what the bones do. Now that serendipitous discovery, again, changed history. We have it in medicine, we have it in airport security, we have it in science. X-rays are a beautiful tool to study materials, objects that we do not see directly. And it was a byproduct, if you will, on that quest that people still were to find out what the nature of electricity is. In fact, people still didn't understand what electricity was because they didn't understand what those molecular rays were made from. But after Röntgen, people wouldn't have to wait for a long time before the mystery would be lifted. And the person lifting the mystery would be another Englishman, Joseph John Thomson, who was born to a working-class family in Manchester, but he was very scientifically apt. He started studying in Manchester and then later on moved to the University of Cambridge. And again, he was one of those people who were good both in mathematics and theoretical physics, but also were excellent experimenters. And Thomson was one who was, from very young age, very interested in the ultimate nature of matter. And he wrote his master's thesis about how Maxwell's vortex idea could maybe be generalized to not only explain electricity, but also explain matter. Maybe matter is nothing but some stable arrangement of vortices in some hypothetical material. And his master's thesis actually won a big prize because it was very unique and original. In 1884, he was still in Cambridge. He became professor at the physics lab there, the Cavendish Laboratory, to which we'll return again many times in the following. And then in 1897, a few years after that, he wrote the textbook on electricity. Okay, he really immersed himself in the science of electricity and what people know and understood about electricity in those days. And so he was uniquely suited, if you will, to make the discovery that we'll see now, because he both knew or was interested in the nature of matter, and he was thoroughly familiar with electricity because he had just written the textbook. So he puts the two together, and he again studies cathode rays. Okay, and he uses a setup much like what other people had used before, a vessel from which he evacuates the air and then has a negative side and a positive side. Cathode rays would come from the negative side and then would hit the far end of the apparatus. But then he does something that people previously didn't do, which is he doesn't try to get the rays out, but he tries to get the instruments in. Okay, so what he does is he connects an instrument, an electrometer, that can measure electric charge. And he connects it to an electrode that he puts inside the chamber, which would normally be missed by the cathode rays, but we'll see in a second what he does with it. Now, the electrometer also has an interesting history because it all goes all the way back to Alessandro Volta. If you remember, the person who invented the battery, he very much was somebody who wanted to do physics by means of measurements. He says, what can be done that's any good if things can't be reduced to degrees and measurements, especially in physics? Okay, he was somebody who really wanted to make everything measurable, and he was the one who invented the electrometer. And it worked in a very, very simple way, as we have already seen by Dufay. If two objects are electrically charged in the same way, they would repel. And so what he did is simply suspend two very thin gold leaves inside a glass jar. And then if he touched it with a body that was positively electrified, all of that positive charge would move onto the gold leaves, and they would simply move apart. Much like in Dufay's case, vitreous electricity pushed apart a glass tube and a gemstone. Now, in Thomson's days, of course, people had significantly furthered the development of this instrument and made it into a precision device, with scales and again, shielding so that no external influences could affect it. And so electric charge was something that could be measured very, very precisely. And so this is what Thomson had hooked up to his chamber. And then he tries the following. Normally, the cathode rays would be set up such that they pass along straight lines. They miss the electrometer, and nothing shows up on the instrument. But then he moves a magnet close to it that is able to deflect the cathode rays so that they would hit that electrode that is connected to the electrometer. And you can see he put the electrode behind a very, very narrow slit so that the rays would only enter that slit and show up on the electrometer if he was able to deflect them in exactly the right spot. Okay, and then he says, whenever the rays were bent such that they hit the electrometer, there was a large charge of negative electricity sent to the instrument. The instrument would react very, very strongly. Okay, gold leaves would spread apart. And then he also says if he deflects them too much, they would sort of miss the slit on the other side, and again, there would be no reading on the instrument. So he says that whatever is happening there, however we twist and deflect the cathode rays by means of the magnets, wherever the cathode rays go, that negative electricity goes. The negative electrification follows the same path as the rays, and this negative electrification is somehow indissolubly connected with the cathode rays itself. And then he thinks, if the cathode rays in some sense are electricity that doesn't go through a wire but that just goes through the empty space in his vessel, he knows a lot about electricity. And in fact, he knows that electricity can also be deflected by electric charges. Dufay even know that. So what he does next is the following experiment. He takes an elongated glass tube. Now he doesn't have a magnet. He doesn't try to deflect it magnetically. He tries to deflect it electrically. Okay, so he puts 2 aluminum plates inside the vessel, and then he charges the aluminum plates either positively or negatively. And he already knows that whatever the rays do is something to do with negative electricity. So if I put positive charge at the bottom and negative charge at the top, which he does by simply hooking up a battery to it, then the rays should be deflected downwards. They would be attracted by the positive side, and they would be repelled by the negative side, and indeed, that's what happened. Then he turns it around, he puts the positive side up and the negative side down, and indeed, the rays would move upwards. And so he puts the 2 facts together. He says, we already know since Faraday's times that magnets deflect electric currents. If you remember, Faraday's original electric motor was a demonstration of that. And we've also already known for a very long time since Dufay that electrical charges either repel or attract depending on the sign. And the same happens to my cathode rays. And so in 1897 he says, the cathode rays, they are deflected by an electrostatic force as if they were negatively electrified. They behave exactly like electricity does. And they're acted on by a magnetic force in exactly the way in which a force would act on a negatively electrified body that moves where the rays move. Okay, so for all practical purposes, I can see no escape from the conclusion that these rays are simply charges of negative electricity that are carried by particles of matter. Okay, something is moving, and he makes that leap and says that electricity is carried by some particle that's moving and that makes up the rays. And that also means that there must be some sort of smallest amount of electricity. A single particle of electricity would be the smallest amount you could have. Now today we call this particle of electricity the electron. Okay, think back to what the ancient Greeks called a piece of amber. They also called it electron. The name stuck, and that's still the name that we have today. But in fact, just presented by this evidence, you might be tempted to think that maybe Thomson made that inference a bit too quickly. He jumped from these rays immediately to the existence of a particle that carries the electricity. Now, obviously, he was very much inclined to think along these lines because of his interest in the nature of matter and something that constitutes matter. But just from these experiments together, he wouldn't have the information to conclude that there is some particle behind it. But he says, assuming that there is a particle, there is a question that arises next, and that is, what are these particles? Are they atoms or molecules? Think back to Crookes's molecular rays. Or are they matter in a still finer state of subdivision? What on earth are these particles? And so he does another experiment. He says, to throw some light on this point, I've made a series of measurements of the ratio of the mass of these particles to the charge carried by it. So he says the following. He says, if there is really a particle of electricity that's behind these cathode rays, and if there's really a particle that makes up these rays, then that particle better have a certain mass, and then if a stream of particle carries electricity, then each particle should carry some part of electricity, should carry some amount of electric charge. So there's a mass, and there's electric charge, and I can try to measure them. And if I'm able to measure them, I'm able to characterize these particles. And so he goes back to the apparatus he had before, where he deflects them magnetically, but now he makes everything more precise. He deflects them magnetically onto a very, very precise point on the glass tube, and he measures how much heat is liberated there. Okay, the particles, if they exist, they would hit the material at that point. Through friction, they would lose their energy and they would generate heat, as we saw from James Joule. And then he would also connect his electrometer at this point to measure how much electric charge was hitting that spot. And if you take both of those measurements together, you could characterize both the electricity and, if you will, the energy, the friction, and so you can measure that ratio of the charge of a single particle to the mass of a single particle. And he tried to do that for different gases inside the tube, and what he would find is that no matter which gas he had, the answer would come out to be always the same. The answer did not depend on the nature of the gas inside the tube, and that means that whatever these particles are, they have nothing whatsoever to do with the gas, because otherwise the answer would not be independent of the gas. In fact, what he measured is really something to do with electricity and nothing to do with the gas itself. The electrons must be something that is not linked to the gas. And that's what he concluded. 1897, electrons are not just molecules of gas. In fact, they're something else. And he ventures a guess because he notices that this ratio, the mass over the charge, is very, very small. And his guess was the smallness of the mass over the charge ratio is, I think, due to the largeness of the charge as well as the smallness of the mass. Okay? So he says, on this view, we have in the cathode rays matter in a new state, a state in which the subdivision of matter is carried very much further than in the ordinary gaseous state. Okay, he says the mass that came out of his experiments is so small it could not possibly be the mass of a gas molecule. It must be something else that's much, much lighter than the gas molecule. And so we're still left with the question, what is electricity? According to Maxwell, electricity is what flows in between rows of vortices that turn in opposite directions. But now, according to Thomson, electricity is something totally different. It's carried by a new kind of particle that's nothing to do with a gas molecule, but is very much lighter than a gas molecule and carries some electric charge. And now both of those are very successful at explaining or describing certain experimental phenomena, and you might be inclined to think, what is the true nature of electricity? Because that's the question we originally set out to answer 3 weeks ago. And the answer to this question, if you will, is very much the same as the answer to what is a table. If you have a table and you ask what is a table, and you ask the Oxford English Dictionary, it would tell you a table is a piece of furniture with a flat top and one or more legs, providing a level surface on which objects may be placed that can be used for purposes as eating, writing, working, or playing games. But if you ask, what really is a table, and you look into a small amount of the table, you would see all of the pores of the wood, if you looked at it through a microscope. And then inside the pores of the wood, there would be water. And water, as we know today, is consisting of oxygen and hydrogen atoms. And if you looked into one of those oxygen atoms, you would see that there is a lot going on inside the atom itself. The atom has a nucleus that's much smaller than the entirety of the atom itself. And then even the nucleus has some complicated structure inside it. And then inside that complicated structure of the nucleus, we again find the electron. So when we ask the question of what is the nature of electricity, it very much depends on who you ask and for what purpose you ask them that question. Very much the same way as I asked what a table is, the answer that you would want to get depends a lot on what you want to do with that answer. But if we really want to understand what electrons are and how they show up in the context of everything else, we need to actually study a different question. Maybe the one that we asked was not the right one. If we ask what is the nature of electricity, maybe we should really ask what is the nature of matter, because electricity, as it turns out, would be just one manifestation of matter. But that's something for next week. Thank you. Yes?
Okay. Now, you described these sophisticated experiments, a lot of them in the late 1800s.
Yes.
My question is concerning inventor, the late so-called Edison.
Right.
Did he have knowledge of these experiments in terms of what he was trying to do, and what was the nature, what means of removing the gas from the tubes that he used compared to the ones that he took?
Very good question. So the question is how if you will, scientific experiments like these interfaced with the big engineering advancements that in electricity that were carried out by Edison, among other people? And the answer is that it always depends a bit. So Edison was clearly somebody who was, I would compare him more to the other engineers that we have seen in the first part of the lectures. If you think back to Newcomen, who built his steam engine, he didn't need to know, or he didn't know for a fact, all of the developments to do with Joseph Black and the nature of heat and such. He was a hands-on person who wanted to put things to use. Very much like Edison, who was a hands-on person who wanted to put things to use and put building blocks together that already existed. Now, vacuum pumps already existed. In fact, he used them to pump the air out of his light bulbs to make the glowing wire last longer, so it wouldn't be burned by the atmosphere that would remain. But he didn't need to push to the absolute boundaries to make the light bulb work. He was sort of happy to stay within, if you will, the comfort zone of well-established instruments and well-established steps in preparing the light bulbs. Other people, the scientists, were pushing the frontiers, and they were preparing the ground for other engineers to follow and then use them. So that's very much that interplay between, if you will, these experiments that really needed the utmost power of what vacuum pumps could do, and that's why Sprengel's mercury pump had such a big impact. But the bulk of the engineering advances, they always happen, if you will, a step or two behind that frontier. What is readily available and was economically viable to do. Because whatever is done first is likely not done in the most optimal way for what concerns efficiency and economy.
And what evacuation method did he use?
He had a mechanical pump also. Yeah. He wouldn't have operated by hand. He would probably have had it electrically operated by a motor. If he put up his assembly line for light bulbs, he wouldn't sort of do it manually. But it would be a mechanical pump in the sense that it would be a piston moving back and forth to extract the air molecules. It wouldn't have needed to be one of these high vacuum pumps that Sprengel and others invented. Yes?
Now they do this in stages. You start with a mechanical pump of 4
That's right.
And then for a vacuum diffusion, usually oil.
That's right.
And that brings it down.
Yeah, that's right. But for a light bulb, you wouldn't even have to go that far. It's true. For scientific needs, today anyways, we can go much, much further down than what even Sprengel's pump could do. And in fact, it turns out today, if you want to go all the way down, you need more than one pump. Because what a pump can do, it can produce, if you will, some pressure differential between the side from which it evacuates and the side into which it expels the gas. Okay, so if you want to get all the way down to a billionth of an atmosphere, you need to do that in stages. You need to put multiple pumps in series.
There's a danger with oil diffusion that happened in the lab here. Somebody had a meter, vac ion meter, we were measuring, and he forgot to put the 4 pump on, so the oil broke up and he turned on it and blew the damn.
So this is actually a good point. So the mercury pump didn't survive until today because mercury is very toxic and we don't use it. But we use something, or until very recently, and for some purposes it's still in use, we use something that's very much like that, but instead of using mercury, it uses a very special vacuum oil. And it heats up the oil so that it would evaporate, and that hot oil steam, if you will, that oil vapor, would be blown out of nozzles at extremely high speeds, and they would again catch the air molecules and sort of export them to the far side of the pump, at which point you would have to take over with some mechanical pump to bring them all the way up to atmospheric pressure.
You don't turn that on, it'll build up oil.
That's right. And in fact, there was a problem like this with an oil diffusion pump. So by the way, an oil diffusion pump, like I just mentioned, doesn't give you the absolute best vacuum because you still have some oil and that oil still can evaporate, and so there's some tendency to take its vapors back into the vessel from which you want to take the air out. So it's not optimal, but it's still widely used for many applications where you don't need the absolute best quality of vacuum. And normally these oil diffusion pumps, they are very nice to use because there is no moving parts other than the oil. So nothing can break, or almost nothing can break. The only thing that can really break is that at the bottom of the pump, there is an electrical heater element that heats up the oil and produces that oil vapor. And in the experiment that I work on in particle physics, we have these oil diffusion pumps because we have large superconducting magnets that are very, very cold, and they're enshrouded in thick layers of insulation, and they're insulated, in fact, by vacuum. Because if there is no air molecules, there is nothing that can transport heat from the cold side of the magnet to the warm side of the room. So if you take the air out, you're able to insulate that magnet very, very well. And we use oil diffusion pumps to keep that insulating vacuum intact. Now in our experiment, these oil diffusion pumps, they're hidden away in the sort of inner heart of the apparatus that's not very easily accessible, or is not accessible at all unless you want to spend several weeks sort of disassembling many things to be able to crawl into it. And so what happened not so long ago is that the one thing failed that could fail in an oil diffusion pump, which is the electrical heater element. And so the vacuum that would keep that magnet cold and operating would start to deteriorate. And now you have a problem, because what do? Right? That oil diffusion pump is connected on a very, very long hose to that mechanical forepump that would bring that exhaust up to atmospheric pressure. And so people were scrambling and they had to find a solution because that pump was no longer working, but it was also not accessible to replace it. So the only thing you could do is put all the pumps that you had on the end of the very, very, very long hose that you could actually get access to. Now that's not optimal, because you can imagine if you suck air through a very, very long hose, you lose a lot of your pumping power. But they put up all the pumping stations that I could find, and it held up. It wasn't optimal, but it held up and it did do the job. So that's to tell you that even today, vacuum science is something that in most cases works and becomes invisible, if you will, on the forefront of science. This is something that happens in the background, but every so often you notice it when it doesn't work. And this was one example.
So an observation and a question, or maybe even two. But the observation first is a good number of years ago, I was exposed to something written by Heinrich Hertz, which struck me powerfully. I don't know that I could quote it verbatim now, but I'm firmly of the belief that the gist of it was, I have no understanding of Maxwell's theory of electromagnetism. And I think you wrote that rather late. For some reason, 1890 just stands in my mind.
Right.
Then the other, I'll try and find the quote and be exact.
Right.
The other thing is, when you were making, the slide you just passed, where you had the Maxwell's connection of electromagnetism to light.
You mean here?
No. Well, the slide's not important. I believe last week when you were talking about how he made the connection, you talked about his idea of the disturbance transmitting through a vacuum, which he connected to the speed of light.
Right.
But today you had when you talked about that, you had an image of a guy standing below a tree looking down through a mirror and whatnot.
Yes.
And I'm curious, I'm not sure that I understand exactly how Maxwell was able to make this connection. And then secondly, I have in the back of my mind, so with the electric waves traveling through the air, I had in the mind that I read somewhere that Tesla, when he was in competition with Edison over which way electricity was going to go, he came up with an idea of transmitting electrical power.
Right. Wirelessly.
Wireless.
Yes.
Yeah. And is that
Correct.
an application of what we were talking about earlier there? And is it feasible, or are you too much loss?
Very good question. So, okay, let's start with the mirror question. So if I understood your question correctly, you were wondering how Maxwell was able to make that connection from his side of the coin, which is all electricity and magnetism, to light. And he went through his math, and as we saw last time, he saw that there was a consequence of the math, which was that you had to have these disturbances. No, okay, I can find them now. It doesn't matter. You would have to have these disturbances that would move at a certain velocity, and that velocity he could compute only based on electrical properties of the air and the magnetic properties of the air, okay, which people had already figured out in experiments much like these ones. Okay, the electric property of the air is effectively hidden in sort of that law that relates the force and the distance. And the magnetic properties of the air would be hidden in a much similar way in the law that connects the force between two coils to the distance of the two coils. Okay, that's what the input that Maxwell used. And based on these measurements that had nothing whatsoever to do with light as such, he was able to infer that that implied the existence of these disturbances that moved at a speed which was impressively close to the speed of light as measured by other people that really used light. And that caused him that coincidence of two numbers that seemed to have nothing whatsoever to do with each other couldn't simply be a coincidence. Like, it had to be signifying something very profound and important. And to him, the consequence was that whatever these disturbances are, it's not something new, but it's something that people had known for a long time, namely it's light. And then that's what Hertz eventually also remarked Maxwell upon, right? Maestro Maxwell was right. There are these waves, he said. But in Hertz's case, they were still the same type of wave, but they were not light waves. They were electromagnetic waves, which are just the same as light, but on a much longer scale. Okay, he was able to walk along the path of the rays in his lecture hall, and he saw the bright, dark pattern in his sparks. So, 1 meter would be roughly, one step, 1 meter would be the distance between two crests of that wave, or two troughs of the wave. Now, in light today, we know the distance between two peaks and two troughs is hundreds of nanometers, a lot smaller, a billion times smaller, in fact, than what Hertz had. But both of them were waves nonetheless, and they were waves of exactly the same nature, electromagnetic waves. And so the mirror that you remarked on, that person was looking into to see the branches of the tree, had the exact same, works in exactly the same way as these iron pillars in Hertz's lecture hall that were reflecting back the electric wave to make his standing wave pattern. A mirror is nothing but a metallic surface covered with a glass sheet, so it's flat. And in a very much the same way, any metal would reflect electromagnetic waves, be it light or be it the much longer Hertzian waves. Sorry, what was your second question?
Well, Tesla and
very good. So wireless transmission of electricity is something that, much like wireless telegraphy, people were very impressed by or very intrigued by, right? If you didn't have to run wires, it would get rid of a lot of the nuisance of it. Unfortunately, it's very difficult, and it doesn't work very well over long distances because you have so much losses that it doesn't really make any sense. You would have to invest so much electrical power to transmit it over a long distance, and so much of that would get lost that it would just be unfeasible. Now, over short distances, it's very feasible. And most of today's phones can in fact be charged wirelessly without plugging in a cable. You just put it down on a charging mat, and there would be a coil in the phone, there would be a coil in that charging mat, and that would charge the phone. Much in the same way that in the two Reese induction coils that we saw, the spark would jump from the top to the bottom. But that would be induction that carries the energy, and it wouldn't be electromagnetic waves, because that is where the losses come in. Yes?
I was surprised. I didn't know about the evolution, so to speak, of Marconi
Right.
struggling with antennas.
Right.
From the bigger than support from a kite.
Yes.
Just imagine how he would have felt if he was allowed to do some time traveling and watch how the antennas have shrunk to what we have on our little cell phones.
Yes.
Just
So,
amazing.
absolutely. So, Mark, absolutely, I agree. Now, the question is, why are antennas today so much smaller than Marconi's antennas? And the answer is, Marconi, it's again to do with the distance between two subsequent peaks or troughs of the wave. It turns out that to make an antenna work well, you got to build an antenna that's roughly of that same size as the distance between the two peaks or the crests of the wave. Or some sort of multiple of that. So what Marconi had, or what Hertz had, were waves, of the order of a meter. And so that's why their antennas had to be of that same size. That's why they fit on a table, or that's why, in his case, he put them all the way up on the top of that pole, or a multiple thereof. Now, the kind of waves that we have in cell phones today, they are much, much faster than these waves in terms of how they oscillate. So in a sense, they're closer, they're in fact getting closer and closer and closer to light, and they're moving further away from these kind of waves. And so the distance between two peaks and crests there is of the order of centimeters, as opposed to a meter. And so now that gives you the ability to build smaller antennas, while still being able to transmit and receive these waves efficiently. That's why today's phones, if you remember, the first cell phones had antennas that you could sort of play. Exactly. So the progress in technology enabled us to work with electricity that's faster and faster and faster, that implies waves that are faster and faster and faster, and that means that they're shorter and shorter and shorter. So the miniaturization, if you will, of electromagnetic waves goes hand in hand with the progress of speeding up electronics. And that's why today's cell phone antennas are so much shorter, or can be so much shorter. Yes?
Could you blow up that last, that round chart you had, I think, of the nucleus?
Yes.
I don't know if you want to say anything about it, but if you leave it there, we can look at it. There it is.
This part?
Yeah, we can, that's the, what is that, the nucleus?
That's all the kinds of constituents that you have in one constituent of a nucleus. So that's the nucleus. And then you see, the nucleus consists of many other, if you will, particles, and we will see how they were discovered next time. And they're just orange and blue here, but then inside of these particles there is again constituents. And if you will, if you ask, what are the constituents of a table, in the end it's the constituents at the bottom of the thing, because everything else is, if you will, a rearrangement of those constituents. And now here is all the constituents that so far we have discovered. Okay, these are what we call today as the fundamental particles of which everything is made. And you see, one of those particles is the particle of electricity, because electricity is in our world, so it better show up here too. And it shows up in the form of the electron at the far sort of bottom of that scale. But we will see how that chart is sort of filled in, because it took a lot of effort and a lot of time to make that happen. Yes, we will be talking about starting next time. Yes.
Okay. We now have chemical analysis of material from the moon and from a satellite. I'm concerned about the iron and the magnet, the amount of what do you call it, a natural magnetic iron relative to non-metallic iron.
Okay.
In both the moon samples and the satellite samples.
Okay. What is the question? I'm not familiar with that. I cannot give you a detailed answer. I haven't read that part of the news. Sorry. Yes.
Was there any appreciation for the speed of light as a constant in Maxwell's equation?
Excellent. So Maxwell he was able to calculate that speed from all of the other experiments. He didn't appreciate at the time the significance of the constancy of the speed of light. Einstein would do that later, and Lorentz would do that later. And they were pleasantly surprised when they found out, when they ran into the significance of the constancy of the speed of light, that the form in which Maxwell's equations were already written by that time naturally consisted with that constancy of the speed of light. Okay, it was built, the constancy of the speed of light was built into Maxwell's equations from the very beginning. Maxwell didn't realize it. People discovered it after the fact. It was not realized by Maxwell. It was realized way after. And this is, again, one of those many points where if you build something to explain a certain fact, and then later on you discover that, it also talks to many of the other ththings that, is very profound. And it talks to, the correctness, if you will, or like something that's true about this. If suddenly it does many more things than what you built it to do. And the constancy of the speed of light was one of those examples. Yes?
If you would like the Thomson's experiment and the idea that it was a discrete particle rather than some continuous phenomenon.
Yes.
So you're saying that Thomson, he's got this hypothesis.
Yes.
It's discrete because
Yes.
chemists are telling us that things tend to be.
So right. So that's a very good question. So at the beginning, Thomson simply had the rays, okay, and he didn't know whether they were sort of discrete or continuous. It's true that by this time, as we'll also see next time, there were many hints coming from chemistry that there is some sort of discreteness to chemical reactions and some discreteness to, whatever matter is made of or gases are made of. Now later, in that last experiment that I showed, Thomson actually bridged that gap because he was able to measure two properties of that particle if it so exists. Okay, he says if there is a particle, it ought to have a mass and it ought to have a certain charge.
There's a ratio between the charge
That's
and
right.
the mass. And the heat is telling us, what is that telling us?
So the heat is telling you, in a sense, how much. So the heat is generated by friction of those particles as they slow down in the gas. And so that means that heat is proportional to the energy that the particles carry, and that speaks not directly, but through sort of an intermediate step with the mass of the particle. Okay, you can imagine if you're like a very heavy particle, it can carry a lot of energy, and would generate a lot of heat. And so the second measurement would talk about the charge, the electrometer measurement. Because it's true. The ratio turned out to be always the same, but he wasn't able at this point to measure them independently. And so it's true that in principle there could be both a continuum of electric charge and a continuum of mass in such a contrived way that the ratio would always end up being the same, right? That wasn't excluded by that simple measurement. Other people later on filled in this gap. But it was a lot, if you will, simpler to suppose. It seems very contrived, right? That if you have some continuity in M and some continuity in E, such that the ratio is always the same, a lot has to happen to make that work, right? So it's not obvious that is what is the case. It's a lot simpler, if you will, to suppose, but not to prove, that there is some discreteness both in M and in E. That's the particle.
Who was it that pointed out that these were straight lines?
Right.
And they couldn't corner.
Right. That was Crookes.
Okay.
Yes.
But that implies it's particulate. Things are ballistic if they go straight.
But water waves also move in straight lines, if you will.
But only for very short wavelength you have rays.
But you didn't know, right?
But
Maybe the wavelengths were very short.
you had no other data.
Right.
Straight lines, you would naturally think it's like somebody threw a ball.
I agree with you, but it can be misleading because light has that exact same property, and for a long time, Newton.
Very short wavelengths.
Well, right, but people, weren't able to measure these wavelengths. They didn't know, right? So it could have been, right? It was beyond their ability to reach at that time. That's true. It could have been.
Well, radio waves make corners.
Oh yeah, because they're absolutely. They do. They do. Yes, for reasons that people also back then didn't appreciate fully. Yes. Yes, please.
If the double slit experiments back in the early 1800s affect the thinking of Thomson or Röntgen because they were so committed to particles, and here we've got some evidence of waves.
So these, very good question. So these double slit experiments that were done first were also done with light, because that's what people could manipulate at ease and they could build double slits for. And in fact, this was a very strong argument against the particulate nature of light. Because if light was a particle, then how could it make all of these wonderful patterns you would observe in a double slit experiment? Whereas with water waves, it's going into a harbor, if you will. The entrance of the harbor is a very narrow slit, and so the water waves would change their appearance as they entered the harbor. Right? So with waves, as the nature of light, you could very easily explain the double slit observation. And so that was in fact an argument against Newton's idea of light being also made of particles. Now, we're getting a bit distracted, it's true, but in fact it turns out that even with electrons, people later on, much later on, in the 1900s, did double slit experiments. And lo and behold, they found that electrons, which here to Thomson appeared to be particles, they also appeared to produce these wave-like phenomena just as light did. So then people were confused again. Is it a particle or is it a wave or is it both? Right, that's the question.
Was that sort of a raging debate during the 1800s?
Very much so. Very much so. Yes?
Who figured out thermoelectric cooling?
That was Seebeck, I believe?
Kind of the opposite of normally you think electricity generates heat.
Right. So that's true. So
Thin ice here.
very good. So
Great cooling.
yes, that's true. So very good point. So in fact, I didn't mention it because I wanted to not get distracted too much, but there is a fifth kind of electricity that already Faraday knew about. So we had in his table, which I can't find now, but Faraday had these four kinds. There was in fact a fifth one that I didn't mention, that was thermal electricity, which is if you take a wire and you make one side hot and one side cold, there would be electricity flowing through the wire as a consequence of the temperature difference. Okay, that electricity could also be generated in the fifth way by making one side hot, the other side cold. Now, the inverse of that is also possible, as somebody called Seebeck pointed out, that if you have the correct situation and you use electricity, you can in fact use it as a heat pump. You can make one side get hot, the other side get cold. That's what then became known as the thermoelectric effect. And that today, in fact, is powering small refrigerators, like camping fridges and such. Okay, last question.
Car radio antennas are very small today, too.
Yes. Yes.
I guess they're a little.
Yes. So, right, very good.
Remember the.
Yes.
We used to have
Yes. Very good. So, I'll come to you in a second. So the question is, if I told you before that, antennas scale with the size of the wave, why are car antennas today so small, whereas they used to be much larger? it's true that if you want to have an antenna that sends and transmits or receives effortlessly, you want to make it be the size of the wave. But today's electronics are a lot more sensitive, and so you can actually get away with not needing the full efficiency of the antenna, so you can also shrink it. So even if the wave doesn't shrink, because radio waves stay the same as they were, even with long car antennas, but you're able to pick out even tinier signals with the electronics that has progressed a lot, so you don't need the full power of the antenna, and you can also make it smaller, to save space and such. It's a trade-off. If you're able to make your electronics more powerful, you can make the antenna shorter, even if the wave itself doesn't change. That's sort of a separate, if you will, engineering trade-off that you can make. Okay, last question.
Could you go back to that circular diagram, the circular table?
The last one?
The one with the particles?
Oh, yeah.
And my question about that, does that represent, do all the particles on that table have a corresponding antiparticle? I see you have the
Yes.
electron circled. And so is the antiparticle for the electron the positron on that table?
Very good. Very good. So the question is, I've shown you all of those particles. It turns out that you can sort of, copy that thing over, because it turns out that most of those particles, not all of them, but most of them, have a twin. And if the electron carries negative electricity, that would be the twin of the electron, that is called the positron, or anti-electron, and that would carry positive electricity. Okay, so it turns out, in fact, all of the particles that carry electricity, there is a second type of that particle with the opposite sign in the electricity. Okay, now it turns out that there are some particles that don't carry electricity, and for which the twin is sort of indistinguishable from the original particle, because there is no change in the sign of the charge that can happen because there is no charge. Okay, so and then it turns out that things are even more complicated than that, because electric charge is not the only charge that there is in nature. There's other charges. And that again makes, there's twins with the other charges that are not electric charge. Okay, so it's a lot more complicated, but the reason why people don't usually show these twins is that they behave in exactly the same way as the original particle. So once you understand that, you will also understand the rest of them, and in that sense, they do not necessarily deserve to be called a separate particle, because they are linked, their properties are intimately linked to those of the original one.
Are there any gaps in there, like the gap for the graviton?
These are all the particles that have been experimentally observed. Gravitons have not yet been experimentally observed. That's why they're not there. Yes. Okay, thanks a lot. See you next week.